Hey, welcome everybody. We're going to go ahead and get started today. We have a guest here who is a longtime supporter of bsac. I'm sure many of you, maybe all of you know Christoph. He's been to many of our reviews in the past and a great friend and supporter of bsac. So Dr. Lang is the Director of Intelligent and Connected Sensors and Systems at Bosch in Sunnyvale, based there in Sunnyvale. From 2000, before he joined Bosch, he's had some other things he was doing over in Germany. He was doing some MEMS gyroscope work at the time. But he's also been in a lot of different areas of integrated circuits and wireless connectivity within Bosch too. He got his doctoral degree in the Technical University of Kaiserslautern. And he has more than 50 patents, and current research applications involve automotive and consumer sensors, medical diagnostics, and the application of AI in sensor systems, which we may hear about today. So let's welcome Christoph back to bsac.
Thank you, John, for the introduction and also for the invite. Also, thanks to Darlene for helping me coordinate all this with all the details that needed to be worked out. And thanks everyone here in the audience, in the room, for coming, and also online for showing interest in this presentation. So when I put this presentation together, I thought, what would be of value for you, especially the students, to get out of this? And I thought I would like to achieve two things. The first one is to show you how complex sensor systems typically are. So complexity I would like to illustrate. And the second thing is that it takes, in many, many cases, an interdisciplinary approach for designing them. Many disciplines have to come together in order to make a system that actually can survive in the market. So those are the 2 points that I would like to illustrate. And with that in mind, I propose the following agenda. So introduction is what we are doing now. I will show one slide about Bosch as a company and then move on to technology. I selected 3 sensor systems in order to show what I mentioned, those 2 points. For each system, I would like to explain the application first and then show the key technology second. So the first system that I picked is electronic stability program. That's kind of a classic for Bosch. It's about vehicle dynamics control, and the key sensor technology is MEMS sensors that many of you might be familiar with. I still put it on here because it also helps set the stage and you get a bit more familiar of what we do at Bosch. Then there's a second area which you might not associate Bosch with. That's medical diagnostics. It's a pretty new topic for us. I'll show you why we believe medical diagnostics at point of care can create value. And then afterwards, I'll go into key technology, bioelectronic interface. And then I'll come back to automotive with keyless entry system. I'll show you how that works. We are currently introducing this into the market, but we are doing research on future generations, trying to use the same platform as sensors, and in order to enable new functions, we use the radios as sensors. And then I would summarize and conclude, and we could have a discussion. So one slide about Bosch. Bosch is a big company. Last year, we made more than 90 billion euros revenue, so about $100 billion. And we have about 430,000 associates worldwide, spread over 60 locations in like 60 countries. And the biggest business sector that we have is mobility solutions. So that's mainly automotive, but also includes some e-bike business. Industrial technology, it's about factory automation. Energy and building, that's heating, climate control, and consumer goods, which is mainly power tools and kitchen appliances. One strong pillar of our technology is MEMS technology, MEMS sensors especially. We have, let me see if I can move this. We have sold more than 15 billion sensors so far. And Bosch, which is not on the slide, but I think it's important to mention, is not publicly traded. So we are actually 94% of the company is held by a charitable foundation. So every year when we make profits, we invest part of it into charitable causes. Like, for example, Bosch has a hospital in Germany, which is a research hospital. So there are medical doctors, professors working and helping patients, but also doing research in order to advance state of the art. And we have about 90,000 people in R&D. Most of them are development engineers, and we have 1,500 in what we call corporate research. So corporate research is supposed to work on things that are further out, prepare new product families, do risky things that, if they work out, also promise high reward. And so I'm one of them. I'm part of the 1,500 corporate researchers, and I'm based here in Sunnyvale, just an hour drive away. And that made it possible in the last years to really collaborate very beneficially with bsac. So I've been here in the Bay Area for 20 years, and since then we have been uninterrupted members of bsac, and we had many, many good collaborations coming out of it. So thanks to all of you for being such good collaborators. With this, I would like to start the technology part. Starting with the electronic stability program, I brought a movie which takes about 2 minutes that explains the application, and then we can go to the key technology afterwards. Start is a bit slow. We tested audio. Should come in a second.
In everyday driving, it's normal for transverse forces to arise. But when you drive a bit too fast or turn the steering wheel, these forces can negatively affect road holding. But the Electronic Stability Program ESP nips that in the bud by controlling the brakes, if necessary the engine, and if need be the transmission as well. ESP comprises the following components: a speed sensor on each wheel. The rotation rate sensor measures the car's rotation around its vertical axis. The steering angle sensor registers the driver's steering intention. From the sensor signals, the control unit computes when and how it has to intervene. The hydraulic unit builds up and reduces the braking pressure in the brakes. What happens during the first steering maneuver? The driver has to swerve quickly to the left. The steering angle sensor transmits this to the ESP control unit. But the rotation rate sensor signals that the car is understeering. That is, it's drifting straight ahead towards the obstacle. In split seconds, ESP brakes the left rear wheel, very briefly and sharply. This produces the desired counteracting force so that the car responds as the driver intended. What happens when you react? When you pull the wheel over to keep the car in the left lane after avoiding the obstacle, the car tends to oversteer, and the rear end tends to break away to the left. The torque to the right is higher than the driver wants. In this case, ESP brakes the left front wheel. The torque is reduced. Instead of going into a skid, the car stays on course, thanks to ESP.
So in this video, there was talk about rotation rate sensor. That's a gyroscope or yaw rate sensor. That's the so-called master sensor of the system. So there are different sensors, wheel speed, steering angle, but the sensor that actually finally decides what the system is supposed to think is the yaw rate sensor. So that's the most important one. And I'll show you one example of a sensor, how that looks like, and then go into more detail. So here you see how they are packaged. If you focus on the picture on the right, you see that there's a molded package with lead frame. And then inside of the package, we have the yaw rate sensor, the gyroscope. That's a purely mechanical part made out of silicon. And then we have an accelerometer right next to it, also purely mechanical. And below we have the ASIC. So they are glued on top of the ASIC and then bonded down to the ASIC. And from the ASIC, bond wires are connected to the lead frame. So now, if you look at the gyro, it makes use of the Coriolis effect. If we have a mass that's moving at a known velocity v and experiences a yaw rate omega, then it will also experience an acceleration, Coriolis acceleration, which basically deflects the mass to the side. And now if we know the velocity or control it, and measure the acceleration or acceleration force, then we can calculate omega. And the way we do it is like this. So we do surface micro-machined gyroscopes. It's based on a silicon substrate. Then we do an epi-poly with a thickness of maybe 11 micrometers in this case, goes up to 20 micrometers. And we do wafer level packaging. So we take another wafer that we bond on top of the surface micro-machined wafer. The wafer that we put on top has a cavity etched into it, and then we can encapsulate vacuum in the order of about 3 millibar. And with this, we get quite a few system aspects. We can generate resonant frequencies in the order of 15 kilohertz, goes up to 30 kilohertz, which makes it pretty robust. We typically employ two masses that we operate in anti-parallel motion, which makes it more robust as well. We have high Q factors in the order of 5,000 in this case that lead to biostability and good noise performance. And we have a tight control of the critical MEMS process steps. So if we look into more detail how this structure actually works, if we focus on the right side, one mass consists out of 3 frames, and they are now illustrated in different colors. So the red frame here, that's the so-called drive frame. And by applying electrostatic forces between the finger structure of this drive frame and fingers that are stationary on top of the silicon chip, we can actually pull this drive frame down in this picture, like towards the bottom of the slide. And if we apply the voltage on the top, we can pull it up. So we can pull it back and forth by applying electrostatic forces. And now in the center, here, there's this yellowish frame. That's the Coriolis frame that moves with the drive frame. It's mechanically coupled and moves with the drive frame up and down. And this will experience now the Coriolis force, which will make it also go sideways if there's yaw rate. And so this yellow frame then is mechanically coupled to the frame, which is gray here in the center. And that's the so-called detection frame, which then moves left and right. And then we can use, again, interdigitized structures here in the center to read out the movement as a capacitive change. And so the electronics that's wrapped around this looks like this. We have our red drive frame here that needs to be driven back and forth at a resonant frequency of the structure, about 15 kilohertz. And in order to do this, we sample the deflection by having a C to V converter that converts capacitive change into voltage. And then we convert it into the digital domain with an A to D converter. We have an automatic gain control, AGC, that has a target amplitude for this structure. And then we couple back via a D to A converter and apply our electrostatic voltages or forces via voltages and drive this red frame up and down. And on the detection side, we again use a C to V converter that measures the detection or deflection of this gray central frame, converted to voltage, converted to digital domain, then we have digital filtering. And in our case, we actually do force feedback. So we couple the loop and feedback voltages to keep this frame still, and we only measure the force that we need to apply to keep it still. And we run a PLL of the drive resonant frequency. So we don't need any external clock. Everything is clocked from the MEMS element and in sync with it. And then we can relatively easily demodulate and then look for the output signal, filter it, correct it for temperature changes, and then apply it on a digital bus. So that's the way the system is set up. I'll show you a few performance characteristics. Electrical sensitivity of such structures is about 2.3 attofarad per degree per second, which is pretty precise and leads to a pretty low resolution limit. Just for the fun of it, we thought, could we measure the rotation of the Earth with such a sensor? And the answer is yes. So if you put a low-pass filter behind with about 5 millihertz, you can actually measure about 3 degrees per hour. and that's enough to sense the rotation of the Earth. And that actually is equivalent to capacitive changes in the order of 2 septofarad. So very precise, and has to work over temperature for automotive range between minus 40 degrees C and about 140 degrees C. One can ask how many such MEMS sensors are in a modern vehicle. The answer is it's about 50 sensors that we have in modern vehicles. Different categories. There's passive safety, for example, acceleration sensors for airbag systems. There's active safety, there's ESP that we just talked about. Powertrain, for example, mass flow sensors. They measure how much gas is flowing into the engine for engine control. And there are comfort functions, for example, again, inertial sensors for navigation. There's also consumer sensors, as we all know, smartphones, hearables. There are accelerometers in earbuds, all the way to gaming. There's one area which is, in our opinion, also a good application field for such micromechanical sensors that I haven't talked about, and that's the medical field. So I would like to motivate why it makes sense to have medical diagnostics at point of care, and then also go all the way down to the interface. So point of care, the pandemic has shown us it's important to do tests right where the patients are. If somebody wants to know if a person has COVID, for example, it's good to have a COVID test right there, and ideally one that's very precise, like a DNA-based test, and not have to send samples to a hospital or like a central lab and wait for 2 days or so to get the results back. And at Bosch, we introduced a platform into the market for point-of-care medical diagnostics. So point-of-care means hospitals, doctors' offices, schools, could also mean people's homes, actually. And this platform is an open platform. So it's a system where partner companies can actually bring their tests and run it on the Bosch platform in a fully automated way. And it consists out of 2 main parts. One is this reader here. It's like a personal computer size that has a slot where you can insert cartridges. And those cartridges are then specific to the test that you want to run. And for running the test, you only need to take a sample, for example, from blood or saliva. You pipette it into this inlet, close the lid, and then insert the cartridge into the reader, and then everything works automatically. You can walk away and you get a result in less than an hour. COVID tests typically take like 30 minutes. And we have those tests for several diseases in the market, and I'll show you what is typically happening on such a cartridge. So let's assume you want to analyze a sample for bacteria. Then you need to prepare the sample, you need to concentrate the bacteria, you need to lyse the cell, so rupture the cell membrane and set the DNA of the bacteria free, extract the DNA and amplify it using PCR, polymerase chain reaction, and then it needs to be detected. And for detection, you always need to know what you're looking for. And then you can make use of the fact that DNA is basically a double strand consisting out of 2 half strands. So if you functionalize your cartridge in a way that a half strand is attached to the surface and the complementary half strand is part of the bacteria DNA, then you can get, in this case, an optical signal and read it out via this reader. So everything happens inside of this cartridge, orchestrated by the reader, fully automatically. So if you look at the range of applications, what I just talked about is the very first kind of application. It's rapid diagnostics, 30 minutes, maybe 1 hour at point of care, using DNA half strands. They're called oligonucleotides. And we typically use about 6 oligonucleotides to determine 1 bacteria, for example. There's another range of applications, which is immunodiagnostics. So that's looking for proteins, not for DNA. And we as Bosch don't have a product in the market yet, but we are doing research in this field. And here it's about detecting proteins. For example, troponin is a marker for stroke. And that's also very important to know at point of care. Then we could drive the very first kind of application a bit further and multiplex it, like having several tests run on one cartridge and having many oligonucleotides spread over a sensor area. For example, way more than 100 different kinds. And that would then enable tests like sepsis, for example. And then there's the last application area, which is oncology. Imagine taking a biopsy of a person and then analyzing the tumor cells for its tumor DNA and detecting what kind of tumor it is and if the tumor has mutated. So as I mentioned, we don't have a test for proteins in the market, but I would like to explain to you what we did in research in order to enable an automatic detection of proteins. And in order to understand this, I would like to show you in half a slide, first the gold standard, and then I'll show you what we do. So gold standard is called ELISA, enzyme-linked immunosorbent assays, and I'll show you how they work. They typically operate on 96 well plates. So I brought one with me here. You can also give it a round. It's a plastic contraption with 96 wells, and you can then pipette electrochemical substances into those wells and have reactions at the same time. So the advantage is that you have 96 different reactions happening at the same time. And the first step is to functionalize each container with antibodies. So they are the starting point. And then the antibodies that are not bound to the surface are washed away, and the sample is added. Sample then binds to the capture antibodies. Unbound sample is washed away. Then a detection antibody is added, incubated for about 2 hours. Unbound detection antibodies are washed away. Then an enzyme is added. And then afterwards, a substrate is added for developing this for another 20 minutes. And then if everything works out, and the sample was in the solution, then you have this sandwich here formed, and you can actually see a color change in one of your containers here. So now we believe this can be made much easier. And we did some research on this. So what we do is, instead of using such a 96 well plate, we use a different substrate that is electrically conductive. And it could be a CMOS chip. We chose to go with a glass slide. So that's a typical glass slide here that you would see under, like if somebody does experiments with under a microscope. If you look at it a bit more carefully, you will actually see that we patterned the glass slide. So there's a layer of ITO, indium tin oxide, on top of the glass slide, which is transparent, but also electrically conductive. And I'll show you what we do with this. So the first step is similar to the standard. We spot capture antibodies with a spotter. Spot size is about 100 micrometers. So we can spot many, like thousands of spots on such a glass slide. And after we have spotted the antibodies, we wash the unbound antibodies away. So we need to do one washing step. And then we add everything else. So we add the sample, detection antibodies that are marked with fluorophores, and let it incubate. And now we don't need to do anything else. We just need to see, are there bound detection antibodies close to the surface? And the way we read this out is we look for fluorophores that are close to the surface. And we want to distinguish fluorophores that are close to the surface from fluorophores that are somewhere in bulk solution. And the way to distinguish them is to change the pH of aqueous solution very close to the surface. Yeah. And this pH change will actually activate the fluorophores that are close to this pH modulation zone, and we can see them, whereas other antibodies and fluorophores that are further away won't show up in our signal. And so for that we use dyes or fluorophores that are pH sensitive. You see there are some that are totally insensitive, like Etto 488, and some like pH-AB, they actually have a pH sensitivity. So at pH of 4.6, there's maximum light emission, and at pH 7.4, there's not much. And so to give you an understanding of how this looks like in experiment, I want to show this slide here. So you see on the center the timeline, and you see on the y-axis pH. So we start with a pH of 7.4. After 20 seconds, we take a snapshot here, optical, and you see it's pretty dark. We continue and try to reduce the pH to something like 4.6 and take 3 snapshots at 35, 40, and 50 seconds, and you see those corresponding pictures, and you see that there are those spots of detection antibodies that are now starting to show a brighter signal than a background, and it's pretty consistent. And then we increase the pH again, and you see darkness again. So as a test, we did an ELISA equivalent and used as a sample CRP, so that's C-reactive protein. It's a test that is done typically actually at annual physicals. Every year I get a CRP test done. It's an infection marker. And we used a concentration of 100 nanogram per milliliter for this example here, which is about 10 times lower concentration than the medical cutoff limit. So it's very low concentration, and we were still able to see this. To show this in more detail, here on the x-axis you see the concentration, and on the y-axis you see the background subtracted signal, and you see 400 nanogram per milliliter, there's a distinguished signal. Even for 1 nanogram per milliliter we can still see a signal, and the cutoff in clinical settings is about 1,000 nanogram per milliliter. We compared it to a standard ELISA and see that we pretty much have the same sensitivity. We are slightly more sensitive, but it's pretty much the same. So with this, we believe that you can actually make an automated test that runs in much less time without any human interaction and do protein-based sensing. Now the question is, how do we modulate pH so close to the surface? And that's what this slide is for, that's currently going around in the room. So that's a slide which is made out of glass, coated with ITO, as I mentioned, also coated with iridium oxide. Here you see a picture. So most of the surface is ITO, and then there's iridium oxide as well. And here you see the spots again, and some electronics that we build in order to control this for prototyping. Here you see how it actually works. So if you look at the glass slide from the side, you see working electrodes in light blue. They are short-circuited, all connected together. And you see the iridium oxide electrode right between them. And now, on top of this is aqueous solution with all the ingredients that I just mentioned, plus one, which is a quinone. So this quinone here has hydrogen atoms that can be set free and become hydrogen protons, and also electrons can be set free. So if this is oxidized, 2 electrons will flow to the working electrode, and hydrogen protons will be set free, which changes the pH. pH goes down. So now by sensing the pH with our iridium oxide sensor, and then applying currents via those working electrodes into the solution, we can actually change the pH via software at the end, electronically, in a closed loop manner. And to show you how that works, I have 2 more graphs. On the left side, you see the iridium oxide sensor, pH on the x-axis, and then sensing electrode voltage on the y-axis. You see that's a pretty good correlation here. And then on the right side, you see how pH is electronically modulated over time. We start at 7.25 or so, go down with a slew rate of 1.36 pH per second, go to a target value, in this case 4.25 or so, and then go up again. As you see that you can actually very conveniently modulate pH in such aqueous solution, which enables the test that I was just talking about. And we believe we can actually do more with this pH modulation. But that's also a question to you. What else could we do with such a modulation technique close to the surface, and it might be also a potential for collaboration between us and you if we find a good application to apply this to. With this, I would like to go to the next application area, which is keyless entry and in-vehicle sensing using radios as sensors. So again, I would like to show a brief video, 1.5 minutes or so, to explain the application, and then I would go into the details.
With the secure system Perfectly Keyless by Bosch, your smartphone becomes the key. In Perfectly Keyless, vehicle and smartphone perform the locking and unlocking of the vehicle reliably and precisely. When the driver gets out, the vehicle independently searches for the key. If the smartphone is removed from the vehicle in the locking zone, the vehicle is locked automatically. A message on the smartphone screen notifies the driver. Perfectly Keyless offers more comfort and flexibility to the driver. The vehicle owner can grant other users access to the vehicle using an app. An additional key is then sent over the cloud. Each user receives their own personal key. Thus, the driver can easily allow others to use the vehicle wherever they are. The system's automatic opening function is also very precise. The smartphone only links up with the system when it is within the communication range of the vehicle. As the smartphone approaches the vehicle and enters the unlocking zone, the vehicle is unlocked automatically. As soon as the vehicle is automatically unlocked, customized settings such as the mirror and seat positions are also triggered. The passive start is another function to make your life easier. When the start-stop button is pressed, a search for the digital key is initiated inside the vehicle. If the search is successful, the engine will start. Perfectly Keyless by Bosch. Comfortable, precise, and secure.
So for many aspects of this application, we needed to know where the cell phone is relative to the car. Like in the first case, if a person approaches the vehicle and it's about to unlock, the system needs to realize that the phone is getting closer and closer to the car. And then for starting the engine, the phone needs to be inside of the car. And for locking the vehicle, the system needs to understand that the person is walking away. So localizing the phone is actually an enabler for this application. And the question is, how do we do it? We equip the car with about 6 radios. And those radios can talk Bluetooth or energy, but they can also talk ultra wideband. And now, as a first step, one of the radios will communicate with the cell phone via ultra wideband, send messages back and forth, and measure time of flight. And then the other radios do the same thing, and we can do triangulation. We can estimate the position of the phone pretty well based on the radio signals of those 6 radios and localize the phone. So that's the enabler for this application. The question is, can we do more with such a system? Can we enable extra functions that go beyond just accessing access to the vehicle? And that's what we are currently working on in research. So imagine we have the same radio at the same vehicle, with the same radios, but no external cell phone involved. We try to make use of what's called CIR, Channel Impulse Response. And if you imagine that transceiver or transmitter sends signal to the receiver, the signal can take different paths, and you see then on the channel impulse response side different peaks. The first peak, tau 1, is basically the shortest path, and then after time tau 2, it's more complicated. So it's multipath signals that we see all in this channel impulse response. And intuitively, you would now imagine that if something happens inside of the vehicle, that should change the impulse responses between those two radios. And we believe that we could use this in order to enable other use cases. For example, occupancy detection. Somebody inside of the car that's not supposed to be in there, like intrusion detection, all the way to detecting children that are left behind. Left behind detection is a big thing, actually comes in Europe. There's a lot of pull for it. And such a technology might at least augment other systems or maybe replace them in detecting children that are left behind. And the question is, how would we do this? I'll step by step try to get there. First show this slide here, showing so intuitively that this might be feasible. So for 5 different states of a car, we looked at the raw CIRs, and the 5 different states are static, like there's nothing happening around the car, nobody inside. Then person outside of the car, pretty close by, 5 centimeters away. Person outside about 100 centimeters away. Front door open and person inside. So those were the 5 states. And for each of those states, we recorded the CIR. And you see this on the left side, you see intuitively there's a change if we plot them one after the other. On the center graph, we did a bit more elaborated signal processing. We recorded first the CIR for the static state as an average. That's our baseline, basically. And then for each situation, we plotted the root mean error, root mean square error between the current state and the recorded static state. And so you see here for those different states, the different results. And we can already guess that there's some opportunity for differentiation, but still some of them are still pretty close by. And then we went to the next step and we said, okay, let's put features on axis. Like in this example here, we put on the x-axis the power of the top peak in the CIR. And on the y-axis, we put the power of the first peak. And then, if I zoom in a bit more, you see that there are clusters of points that we see. Like for some states, now for example, this blue one here, which is front window open, it's pretty isolated. Or the red one is front door open, it's isolated. And some others are pretty close by. And there's one that's all over the place, which is person in front. But intuitively, you get a sense that you might actually be able to understand what's happening in there. So then we went even further and did the following. We over-instrumented the car. We put not only 6 radios, but we put 14 radios. And well knowing that this will not go like this into a product, but we just wanted to get a sense for how this could work. And so we have 6 radios outside, those are the blue dots, and we have 8 radios inside. It didn't take long to find out that for interior sensing, the external nodes don't help much. So we actually took them away pretty soon, and we were left with 8 nodes inside. And then we started communicating around. So we picked a transmitter node, for example, this one, node 0, and then we communicated with all the receivers around and recorded signals. So we followed this path here, transceiver selection. Then we did an upsampling of the CIR alignment. And then for each receiver, we did basically a 2-step approach. Like for each receiver, we did a maximum likelihood-based state pruning, which basically means each receiver says which state the car most likely is in. And then as a second step, we did multipath profile-based classifier, which is like a random forest algorithm, basically, nothing special. Standard machine learning, no neural networks, and then eventually estimated the car state. And here I'll show you what we tested this in. we put the car into 7 locations, for example, and here on the right side, you see the pictures that correspond to it. Like we put it into our garage, we put it outside on the parking lot with other cars around it, we put it outside just by itself. And in each location, we tested 8 different states. One is empty car, front door open, front window open, all the way to person in the front, person in the back. And if you look at the confusion matrix for this, averaged over all 7 locations, you see that this is actually pretty good. Like here, you see the true states, here you see the predicted states, and you see confusion matrix. And if we look at average over all 7 locations, it's about 98%. But that's with always 1 transmitter node and 7 receivers. So we use 8 nodes total. The question is, can we reduce the number of nodes? So on the right side here, you see a graph where, see if I can find this here. That's difficult. It's hidden in my Zoom window here. On the very right side, you see the case with 7 receiver nodes, and that's basically equivalent to what you see on the left. It's the same situation, and it's about 98% accuracy. And then we started reducing the number of receiver nodes. For example, for 3 receiver nodes here, you see 2 values. One value in blue, that's the best configuration of receiver nodes. And it's something, it's more than 90%. And then in red, you always see the mean configuration, permutating all the configurations and see how good that works. So if you look at the blue line, we see that 94% accuracy with just 3 nodes, which makes us hopeful that in real products, where the total number of radios per car is about 6, we could actually pull this off. And that's what we are currently working on. So we are also employing neural networks now, making it more robust, looking at corner cases, and try to optimize this further. And it might be also an area of collaboration that between wireless experts here and us. With this, I would like to summarize and conclude. So I hope I could show you 3 sensor systems and the key technologies behind them. Started with electronic stability program, including MEMS inertial sensors, then medical diagnostics, including what we call single-step ELISA, using pH modulation, and then went to keyless entry using radios as sensors to do in-vehicle sensing. And what I try to bring across is that interdisciplinary research is key. I feel there are many disciplines that need to come together in order to pull such sensor systems off. And one advice to the students is take the opportunities to also learn outside of your core areas. And it's clear that you need to be strong in your core areas, but if you have a chance to look left and right a bit and at least learn the language of adjacent disciplines, I feel that can help in your professional life at the company or maybe in academia going forward. And I also wanted to show the complexity of such systems. And again, there are collaboration opportunities in several areas here. With this, I would like to thank everyone for your attention and opening up to discussion.
Okay, we have questions?
Yes, I'm Professor. And also my first time to know that we need at least 15 times per these cars.
Yeah.
And I want to know if, like, you mentioned that here we use machine learning to predict the car state, car state prediction. What kind of machine learning we use?
I think there was first a comment that it's surprising to see 50 different MEMS sensors in vehicles, but then the real question was about what kind of machine learning we use in order to predict the state of the car. So that we have different approaches. Like we started with classical machine learning, like random forest, for example, played a role here. But then we believe that neural networks also can help, especially when it comes to dealing with corner cases. And what we found is that the networks themselves, and I think that's the core of your question, doesn't matter so much. It's actually more the data that we put into them, which matters. And Yeah, exactly. And so if you figure out data for one car, then the question is how would it apply to the next car? So exactly. And so that's the core of our research challenge right now, how to produce data quickly that we can feed into those networks. And it's not so clear. So one way is to also think about synthesizing data. And but then of course there's a danger, if you put garbage in, you get garbage out. And so it's really about curating the data very well. We try to make use of symmetries. You know, if you figure out, let's say, the left half of a car, you could actually synthesize to a certain degree what's happening on the right side because there's symmetries. So that's something. Then we also try to use physics in order to stretch certain parts of the input data. Like for a bigger car, we would stretch it a bit, but that is active research. Yeah. So we are looking into this. The answer is still open. So we have efforts on synthetic data generation, and could be again a collaboration topic. And it's not so clear how helpful it really will be. Oh, so that also ranges. Eventually, it has to go on an ARM processor, M33 kind of setup. But we currently start with more resources, like on a laptop. We simulate this.
I was really interested about the CIR stuff. So my understanding is usually the CIR is captured when you have a signal that is sent, right, and then the receiver already knows what that signal is, and it kind of compares that. So that's my understanding of it. And usually I did a project on this using Wi-Fi, and it's not really Bluetooth in this case.
We use ultra wideband, yeah, for the CIR. Yeah.
So how does it compare? Is it like, what's the example of Wi-Fi? Because in Wi-Fi usually you look at like sub-cables and you look at your right? So I was wondering if you can help.
It's pretty, it starts with the question, can you get access to it? Is it open? And that is not always the case, but you have to find the right radios where you can actually access it. And that's also for Wi-Fi, it's similar. And so you need to get access to it. And then, but then once you get access, it's pretty comparable, yes. So you have a bandwidth over 500 megahertz. And you can get access to this data and then plot it over time.
Someone walking behind a wall can attack those things.
Yeah.
You don't really have a true ground truth.
Yeah.
And so I was really impressed by the fact that statics is
yeah.
Have you tried maybe combining two cases together?
Yeah, so we tried several scenarios, combined them, and for each of them we recorded the data. So we have a huge database now, and then we can, based on this database, we can now try out different algorithms with the raw data being stored. And we generated this also more or less automatically. So we have a motion capture system. So we have a system that always uses a different modality. It's optical, that always knows exactly where the radios are, and then we have used this to create ground truth, and then we record all the data and then do those permutations.
Any other questions?
So it seems like for the acid that you're developing this pH contribution technology for, that assay is not reversible, right? Once.
Yes.
So, but technology is something that can be used over a long time. It was chaotically.
Yes.
Characterize that, and yeah.
So the question was if the pH modulation technology is reversible and if it can be used over longer periods of time. Yeah, the answer is yes. Yeah. So it depends on those quinones. Those quinones need to, like those are the chemicals that can take up electrons and protons. They seem to be pretty okay. We developed our own version of quinones, so it's not like we found out if you go with quinones that you just buy off the shelf, there might be an issue. But luckily, we have a synthetic chemist in our interdisciplinary team who was able to do a modification on the quinones, and they are like they last for a long time, so that's not an issue. And pH can go up and down. Like we modulate pH between 3 and 10, so that's like 7 orders of magnitude. Yeah. Yes, that's a good question. And
Repeat the question.
oh yeah, so the question was about security, and the danger that the students saw is that if somebody comes with a repeater and mimics basically the communication between the key and the car, can open the car. And so there are several things you can do in order to prevent this. One advantage that ultra-wideband brings is you can measure the distance. So if with older technology, it's a bit more easy for the bad person because the distance is not really measured in the system easily. But with ultra-wideband, the system always checks if the key is actually close to the car. And if that's not the case, then it wouldn't work. So even if there's a repeater in between, you know that the original key is further away. So ultra-wideband helps with security because of being able to measure distance via time of flight. One big advantage that ultra-wideband brings into this area. If somebody steals your phone, then you're so it's still the same. It's like stealing your key, but you can actually then take the key away. So that's exactly. So exactly. So you can take the key away. So it's better than losing your conventional key. But then if somebody steals your phone and opens the car before you can do anything, that's still a problem. Yeah. But you can actually do this, like this key sharing is also helpful if you just quickly want to give somebody access to the trunk of your car, for example. You can give the key to your friend puts something into the trunk, and then you take the key away, and then this phone cannot help anymore.
So when it detects that you're out of the locking zone, that's when it sends a notification. That notification using ultra-wideband, because like you might get notification be out of that zone.
Yeah. So another. So the question was, what happens if the phone leaves the locking zone, and how is notification actually being sent? And so there are the two things. One is the locking zone can be defined with a radius which is smaller than the radius of the ultra-wideband communication. So you can still, like, once you hit this radius, you can, it's a bit more than 2 meters actually, it's not so far. And then you can send the message while ultra-wideband is still working. But so I think that answers your question, but to add one comment to it, for initiating everything, we typically use Bluetooth Low Energy. So that starts the communication, gets it going, and then we use ultra-wideband mainly for the ranging.
Okay, any other questions?
Talking about the car state estimation, so you mentioned that you can reduce the number of these nodes and still get a good result. But in the configuration, I know that you always like fix one node at the TX and
Yes.
the other at RX. So is it possible like you can switch the TX like for example we have 3 nodes. Sometimes node 1 at TX. The sensor run and then node TX sensor run.
Yes. So that's possible, and those are the different permutations. Nevertheless, it turned out that using the node in the center here, the node 0 here, as a transmitter is a good way to start. Because intuitively, I mean, it's right in the center, and you can pretty much cover the interior well. But we did the full permutation. Yeah. So you can imagine all combinations.
Okay, one last question.
For the biosensor, it obviously you're using optical sensing. Can you like elaborate on why optical versus say electrochemical or magnetic? And then it also seems like this pH modulation was a solution to make the optical sensing work, right? Modulating the fluorophore activity.
Yeah.
So which came first? Was it like you chose optical for a spec reason and then devised this pH sensitive fluorophore or?
Yeah. So optical is, first of all, it's pretty close to what people are currently doing in the lab, but that's not an argument for doing it. In this case, for the product that we have in the market, it's an optical sensor as well. We chose to not electrify the cartridge, actually. So those cartridges, there's no electronics in those cartridges that are currently in our products. Makes it easier to make them and also less costly. And so therefore, optical readout is good. We are thinking of electrifying the cartridges. That could also then lead to electrical readouts. We might actually save the whole optics in the reader, and it could be a solution. Yes. And so let me see. Let me show this. Just as a step, like an intermediate step, actually, I didn't really talk about this. So we announced a product that is based on a MEMS chip, which is optical. So this is a MEMS silicon chip. It's about the size of my fingernail, and it has about 256 wells. It's like a 96 well plate, just in MEMS. And then we can run several reactions in parallel in this chip. So it's basically makes it useful for multiplexing. And here you see a picture of such a MEMS chip from the top with basically many, many reactions showing optical signal. And so that can be read out without electrical contact in parallel, just with an optical reader. So that's pretty convenient, and it also fits into our product flow. So the way it's currently set up, you can actually run those new cartridges with the old machines. So it's backward compatible, basically. So that's one reason for staying optical with this approach. But in theory, yes, could also be electrical readout.
Okay, let's thank our speaker again.
Thank you.